So thank you very much for inviting me. It's a pleasure to be here. I'm going to talk about WG4. It's probably the less focused working group of Gaia. The title is Gaia Fundamentals, Time and Space, so you can have an idea of what are we talking about. It's very broad. I am the leader of this working group with Maria Teresa Crosta, that she's here. And my idea here, because also of the title of this meeting, to try to inspire next generations. My point here is not only about what we have been doing, but also what is the future with the next data releases, and also, of course, I picked some results that I think that are quite interesting. It's not an exhaustive list, so I'm biased. My colleagues, please don't be angry with me because I'm not going to list everything. So, beginning. Of course, we all know that Gaia is about making the best ever three-dimensional dynamical map of the galaxy. But the fact is that this mission has an autonomous onboard detection. So everything that is a kind of point-like, or at least not more extended than, say, 200 milliarc seconds, and is sufficiently bright, say, brighter than 2021, is observed and is transmitted. So this means that not only stars are going to be observed and transmitted, but there is a range of objects, from solar system objects to extragalactic objects, that are also detected and transmitted. And here you have in data release 2, for instance, that more than 4,000 objects from the solar system were detected and published. And in the R3, we have more than 1.5 million of extragalactic sources that also detected and published. So Gaia has been a very, very successful mission, not only for stellar and star-related stuff, but also for things that, for instance, in terms of extragalactic stuff, people were perhaps a little bit more skeptical. And the fact is that Gaia has been a very powerful mission in these areas. Now, being WG4, it's also very nice because my colleagues from 1, 2, and 3 have putting my life easier. And I'm going to show you just an example of something that is not, well, it's related with stars, but it's not completely, it's not a star, was this very nice work from Pierre Kerveil and colleagues, that they pinpointed a system that has probably an exoplanet in this system. Alessandro Sossetti talks about this result, and so I'm not going to repeat, but essentially they are taking advantages of differences in proper motion of the stars among different epochs, and pinpointing astrometric bubbles of the stars, and getting from there the indirect detection of exoplanets. So very nice work. Now, apart from being an all skies mission, it's also a multi-epoch mission. So, and this opens a huge number of opportunities to study phenomena related with variability. Sorry, and also due to the way that Gaia scans the sky, we can have variability from the scales of seconds, hours to weeks. So this covers quite a nice range of possibilities. Now, as you know, in first place, Gaia was thought to be a 5-year mission, and in that scenario, each object was going to be observed a kind of 70 times, depending on the position of the object in the sky. Now, we know that, fortunately, the mission has been in quite good health and is going probably to be at least 10 years of acquiring data. So, for instance, in DR5, the expectation is that the data that is going to be released is going to be based on 10 years of data and of mission. And this is really a luxurious data set. The DR4, the expectation is that astrometry and photometry data are going to be released with time series. And again, this is really a luxurious data set. Okay. I'm just pointing here that from 2016, there is a dedicated platform that collects all phenomena, all data, all transients. It's called transient alert. So everything that changes flux from the last transit comes to this database, and actually the database is quite large. And so there are, of course, the expected suspects, supernovae, novae, things like that, but and AJN. But there is also a large list of objects that we really don't know what they are. So this opens also quite a nice venue for some work. So WG4 scientific goals are a kind of related with different aspects that are non-stellar related, or that are related with variable phenomena, intrinsic or extrinsic, and also with fundamental physics. And our group is divided in four groups with different scientific goals. We have reference frames in fundamental physics with Gaia, and that's the leader is Maria Teresa Crosta. We have gravitational waves with Gaia, and that's the leader is Peter Jonker. We have calibrating the distance scale. That's really something crucial, because having the sky in 2 dimensions does not give us too much information. You really need distance to know the intrinsic properties of the object. So distance is very important. And the transient sky is with me. Beginning by, I'm just going to pick some work related with each of these subjects, and also things that are going to work that is going to be also done, but in the future, not near future, but long future. Okay, beginning by the reference frames and fundamental physics with Gaia. What we have here, the thing is, when we go to micro arcsecond level of accuracy, gravitational perturbations are relevant to understand the path of the photons. And so general relativity has to be in the core of the Gaia data processing to be at the level that scientific products of Gaia have. There are different groups working on this. I'm going to show here results from Torino group, Maria Teresa's group. Sergio Cleonard also has been doing a lot of work on this. Give you here 2 examples. So we have to take in account the gravitational effects due to the sun and solar system bodies at the solar system scale. Jupiter, of course, is one of a big mass body. And what they have been doing, it's a kind of Eddington-like experiment plus, where they are investigating the deflection of the light by the presence of Jupiter, and they have very the questions about this, I point them to Maria Teresa, that she's here. And they are also looking for the gravitational effects at a larger scale, at Milky Way scale, looking to the Milky Way. It's kind of local cosmological laboratory. So we have very great distances in kinematics, and we can compare this with models like lambda cold dark matter model or other model that applies better to what we see. And the next talk by William, he's going to talk a little bit more about this gravitational astrometry era. They also have made quite a nice outreach um, stuff. And this is about Aquino, the photon who fell to Gaia. So again, this is a work in framework of a dissemination that's about the meaning of light. And if you are interested, please talk with Maria Teresa about this. Moving to gravitational waves in Gaia, one of the great things that the new generation of researchers has is that they are really in the middle of a new, completely different paradigm in terms of astrophysics. The detection of gravitational waves did put us in the multi-messenger astrophysics, a new thing. Now we can understand the universe from other sides, not only from the electromagnetic side. So I think that's very, very interesting times. And Gaia can help us with this new multi-messenger era by, in an indirect way, detect gravitational waves. And how can we do this? Well, one of the ways that we can do is to be prepared, and Peter Jonker and colleagues have been doing this. Be prepared to pinpoint optical counterparts that others that others can detect of gravitational waves. And LIGO Virgo, next run is going to be towards the end of this year. So here the thing is, if they detect a gravitational wave, Gaia can be prepared to try to trace the optical counterpart. Of course, having just a gravitational wave tells you very little about what is the phenomena that origins is the origin of that gravitational wave. One work that I thought that was very interesting, and these are not people from WG4, but nevertheless it's an idea that the youngers can pick and think about it, is that the level of accuracy of Gaia data can be pushed at certain limits. And what this group here is doing is saying, well, look, if a gravitational wave crosses the neighborhood of Earth, it is going to produce a kind of a jitter in the position of the stars. So a kind of oscillating pattern. And this is a kind of the same thing that pulsar time arrays are doing or pretend to do in the radio band. The idea is that the signal from pulsars, if it's perturbed by a crossing gravitational wave, that signal is going to arrive us with a change in time. So here it's not that change in time, but it's the position of stars that can jitter. And so it's also a very nice way of trying to detect gravitational waves. Now, moving to calibrating distance scale, as I said, this is a crucial thing to astronomy in general. And so, of course, we can do it by parallax. Parallax is the cleanest way of getting a distance, of course, because you don't have to assume nothing about the source. You just it's just a geometrical effect, so it's very clean, but has the limitations of the distance that you can probe. So we can probe kiloparsec distances, not megaparsec distance. So we have other tools. One of them, of course, are the standard the variable stars via the as standard candles, and in this group, people have been looking for luminosity period luminosity period relations. And in particular, the group of Tatiana have been looking for our Lyra stars. Giselle already mentioned this before. So they are getting very accurate relations with metallicity for RR Lyras that are in the field and globular cluster Lyras. Transient sky. Well, we have a huge different type of phenomena that varies. And here, this plot here shows you the different phenomena from nova, supernovae to AGNs, and also the range of variability in terms of output of brightness, and also the time that the time scale of that kind of phenomena. I'm picking, because it's my area of research, AGN here, and also Gaia has been doing quite good stuff with AGN. One of the most important things actually is the celestial reference frame. The celestial reference frame that we have been lately using, it's based on the radio. So it's based on the observations of AGNs in the radio. Why? Because with interferometry, with very large baseline interferometry, we can get very accurate positions, as accurate as Gaia. And why AGNs? Well, AGNs do not move. They do not show proper motion. If an AGN shows proper motion, it's not an AGN. So they are cosmic objects, and so they are very good for this kind of stuff. And Gaia, what has been doing is to observe also AGNs and construct the celestial reference frame, but in the optical. And this is done by observing a fraction of objects that are also radio detected. The thing is, not all the objects that are radio detected are Gaia detected, because sometimes they are quite faint, and Gaia has its limits in flux. And then I can build a reference frame in the radio, I can build a reference frame in the optical, but at some point I have to do the alignment. And for that, again, the AGNs are crucial, because we can pick the best ones and observe them in both bands of the electromagnetic spectrum, and then do the alignment. Now I'm just going to show you a couple of subjects that that have been using Gaia. Actually, it's this one. This is a work from Kovalev and colleagues, and what they have been doing is to compare the photocenter of AGNs in the radio and with Gaia. And they got these very nice results that they see offsets in the photocenters, and these offsets are related with jets, or at least we think that are related with components in the jet. And there is this has consequences for many aspects of what we believe in the center of about the central engine of AGNs. Another work, and this is related with me. One of the things that we assume it's commonly accepted in terms of hierarchical formation and evolution of the galaxies is if we have galaxies that have both a supermassive black hole in their center. At some point, we know that galaxies can merge, and if they merge, at some point, these black black holes are going also to merge, and after merging and getting one supermassive black hole, the fact is that is expecting that gravitational waves are emitted, and this kicks the supermassive black hole from the initial position. So we are we think that we should see um, binary systems when they are very close by of supermassive black holes and kicked supermassive black holes. Now, the problem is good for theory, but we have been failing to detect, at least in a statistical way, these objects. So they are really, really difficult to pinpoint. And what we propose to do is to take advantage of the next big machine, that is the square kilometer array. So it's an interferometer in the radio that is going to be great in terms um, of sensibility and all-sky surveys, but does not have the resolution that we need. But that can be fixed by operating SKA with VLBI, and we have both of the best walls. And in combination with Gaia, we think that we can try to pinpoint these systems, because with Gaia, we will try to pinpoint the host galaxy, and in the radio, we will try to pinpoint the supermassive black hole. And by comparing them, we can try to find the very difficult kicked supermassive black holes. So this is one of the projects that is part of the portfolio of SKA and VLBI. If there is an area that this next data release has going to be an impact, is exactly in the AGN research, because new products are going to appear in this data release, and some of them are really related with this area. So not only the number of AGNs is massive for a mission that was not thought to be AGN related, but also because we are going to have for the first time a huge amount of spectra. It's low resolution spectra, true, but it's massive, and we can get redshifts, and maybe we can get some kind of information on the emission lines. And on top of that, also Gaia detected also in a fraction of these objects the host galaxy, and not only detected but could get information from it, from the profile of the galaxy. So we have also information about the host galaxy. Okay, so let me just finish by talking about what is the networking and collaborations inside this working group. And not only in this working group, of course, all my colleagues said the same thing as I'm going to say. COVID had a major impact in the cost action that is about networking, and we couldn't do it. One of the things that I really want to stress is about the short-term scientific missions. This is really a powerful tool in the actions. People, please apply. It's really, really simple. It's straightforward process. And this gives you the opportunity to travel and to be with your colleagues and do stuff Gaia related, of course. On the workshops, this was probably the last workshop before COVID, was December 2019. We were there. It was very nice in the
Sonia, sorry.
one. So this was on dynamical view of the sky. It was a broad workshop from solar system objects to AGNs, and then life got complicated, and we didn't know in this picture how complicated life would come. And then the next one, sorry, Giselle, I think that already mentioned this workshop was completely online. And now we have two new workshops. Despina already talked about this one. Is going to be in September. Thank you. In September in Athens. It's going to be on galaxies behind the Milky Way. And we are organizing one in Coimbra, also now in October. And it's going to be about the transient sky, so variability phenomena, etc. We will announce this soon, so please check the cost action page for details, and I'll stop here. You see, I behaved.
Thank you very much. Thank you. Perfect timing, absolutely. Is there any question? Yes, please.
There's another result that I would like to highlight.
Sure.
When you have very good astrometry, you can start thinking about the second time derivative. And so you go beyond proper motions to acceleration.
Sure.
I always thought that this was science fiction and it will be done in the post-Gaia era. Well, Gaia did it already. They measured the acceleration, local acceleration towards the center of the galaxy, which is a vector. It's not just the magnitude of the direction. Now, that's very good because modelers like to use potentials. But potential is not an observable. You can only measure difference in potential, not the real potential. Whereas the force field is something you can measure. And Gaia was able to do it. It's only one point in the galaxy, it's the solar neighborhood. But it's a very hard point. All dynamical models have to satisfy this. So to me, as a dynamicist, this is the greatest result from Gaia. Now, moving beyond Gaia, I think if you want to go to a microarc second or sub-microarc second, now you're going to have problems with the reference frame.
Yep.
Because now the AGNs are going, you have the quasar variability. So what do you know about that? Are people thinking about this?
Oh yeah, I have been thinking about this from, I think, more than 10 years ago. No. And the fact that we say that the AGNs are so unmuting things, it's not true because they have jets and the jets move and everything. The thing here is to get the most boring AGNs you can find, so the ones that do not do anything at all, and these are going to be your fiducial sources for the reference frames. The others are going to be the interesting ones for doing science.
So these are very exciting times.
Oh yes, definitely, definitely, I agree.
Okay, question, Emilio.
Sonia, thank you very much for this inspiring talk.
Good.
All right. So my question, because I didn't realize the possibility to measure or to observe or to detect gravitational wave by the changing position of motion in the solar neighborhood. Do you estimate the sensitivity level you can find in the position of the
I didn't, because this is not my work at all, but these guys.
The idea is to see a pattern. But it's homological gravitational waves, not background stochastic background. So it's vectorial, it's analysis by vectorial spherical models. So it's Mach seconds, super Mach seconds, because the main observable here is an extra shift in the light direction into the casting gravitational waves. So they in this book they combine all Gaia data and see this pattern.
Fantastic.
It's really nice. Yeah.
Yes.
I thought that this was mind blowing.
Yes. Any other question? Yes, please.
With respect to
Pedro?
the distance ladder, I think now there is a tension between the determination of the Hubble constant from the microwave background and the supernova.
Yep.
Would you be able to shed some light?
No. Sorry, it's not my. Don't know if you want to.
Sorry, I didn't catch the word.
The H naught tension.
It's no sense. Yeah.
Yep.
Okay, we are investigating also this Gaia, actually with the relativistic model working with Gaia. We are working in a special team that Gisela lead, EC team, and we are probably checking also with there are systematics in theoretical models using some residual on the distances. For example, if you put these distances in the framework of general relativity and then to apply some distance scales. So this is also part of the so we can consider H naught tension also from the relativistic model at the very core of the Gaia data processing and to see if there are some systematics used in the modelization.
Thank you. Do we have, yes, please, last one, huh?
It's just a comment of a positive comment in the sense that you mentioned that the COVID has affected a lot the networking activities. And now we know that there is a chance to be extended. So
Yeah.
it's possible that the cost action could be extended by 6 months, something that we have to apply, submit, and be approved. But it could be the possibility to have an extension of the 6 months. And this means that all the activities can be extended. And I think it's a positive message.
Yes, good news. So thank you very much. We thank our speaker again.